All right, so let's get started here. So probably spent a little more time kind of going over the syllabus and things last class than I maybe needed to, but I think it's good to kind of set us up for the rest of the semester. Today we'll kind of jump into the first kind of topics and material. I'll try to go relatively slow, but kind of to start out, I want to mention anytime I show you, so this is right business statistics. I would probably call it applied statistics. We'll be doing a lot of examples that are look very business related. We'll have some that maybe don't, right? Now, the ones that don't, I would argue that really anything could be business related. So for example, today we'll look at some data about leading causes of death. Well, this doesn't sound like a very business related example, right? We're not talking about anything, that seems related to them. But if you work in the healthcare industry, leading causes of death is your business, right? So I'll try to give you a glimpse at a lot of different topics because, depending on, you could have the same position at, a myriad of different companies, and all those companies specialize in a different area, right? So I want to make sure that we're kind of looking at everything. Now, I'll use some data sources more than others. So I just mentioned a few here, like I've got labor statistics. We'll look at some income stuff throughout the semester. We might do with some finance data, like looking at stock prices. We've got the Fed, who gives us like county level demographic information or unemployment rates. And then sometimes I'll just use surveys. So surveys of individuals' behaviors, right? So we'll get a lot of different types or kind of areas of data. And really the goal that I have in this class is, yeah, it's great that we can do a lot of the computation, come up with these different statistics, but it's more important about how can I use these statistics to make more optimal decisions for the future, right? Also, I want you to look at things with a little more critical, a little more critically, like anytime you see something put out there that is some type of statistic, if we have a good enough knowledge about how those statistics are computed, some of the other topics that we address, we can start to be a little bit critical or kind of scrutinize those a little bit and maybe be able to kind of call people on their BS a little. So some examples of that, just kind of start us out, would be something like, you see it's reported that California has more teachers than Arizona. And so then this source concludes that California cares more about their children's education. So what's wrong with this statement?
California's got a really large population.
Yeah, pray to God they have more teachers, right? They've got a lot more kids, right? So it's not necessarily that this statement is even wrong, but I'm using the wrong statistic. What statistic might allow me to make this statement? Teachers per student, maybe, right? If California had more teachers per student or per capita, then maybe I could make that statement, right? So I'm using the wrong statistic here, right? Also, anytime we see data that's censored, that's like over a certain time block, but think about why. So for the example I'll give you here, and I'll drop some sports examples in here occasionally just because there's a lot of data out there. It's very easy to obtain. But this one, doesn't matter if it's a sport example. So small versus large market teams. Large markets are just ones that have more people. So New York, Chicago, LA, but they have more people. So they're able to kind of have higher demand, set higher prices. They have more money to get better quality players. So we expect that large market teams typically will do better. Right? However, if someone told you 6 out of the last 10 World Series were won by a small market team, so money doesn't buy championships, right? Well, why do you think they stopped at 10? What's probably true if you went back to the 11th year? Go back to the 11th year and a small market team did win. Well, then why wouldn't they be using 7 out of 11? That's better than 6 out of 10. So it's probably true that in the 11th year, a large market team won. So 6 out of 11 is worse than 6 out of 10. And maybe if I go back to the 12th year, well, now it's only 6 out of 12, right? So there's probably a reason why they stopped at the past 10 years, right? Because that was probably the best statistic they could get, or the highest kind of proportion of wins from small market teams, right? So anytime you see data stop at a certain year, they only go back 10 or they go back, it's really telling if it's something weird, like they're like, oh, in the last 12 years, you're like, that's not even like a nice round number. Why'd you choose the last 12? There's probably a reason, right? Another one, this was I think, a good example of thinking about the bias that exists in collecting data. So a study found that 90% of bar fight deaths were the individual who started the fight, right? So let's think about if there's a death in a bar fight, we'll kind of think about two people. So there's only one person remaining. So the only person we can ask about who started the fight, if there weren't anyone around, is the person who's left. So are they going to admit to starting the fight that led to someone dying? I mean, they're basically admitting to manslaughter there. So probably not, right? The fact that this isn't 100%, it would be crazy, right? So always think about like, where are we collecting the data from, right? Who's reporting the data to us and what biases might exist in that reporting. In fact, later on in the semester, we'll spend like a whole class or maybe even 2 classes talking about the different biases that exist when we're collecting data. Okay? And the last one is kind of the age-old stats example, but higher ice cream sales are strongly positively correlated with higher drowning deaths, right? So ice cream, eating ice cream is causing people to drown, right, or to die. Why doesn't this make any sense? I mean, first of all, it seems ludicrous. I mean, just intuitively. But what are we missing here? It's not that.
Maybe like in the summer, people eat more ice cream and then they drown.
Exactly, right? There's more people swimming and more people buying ice cream when it's hot out. There's this third component, this third factor that's driving both of these. It's not that one of these is causing the other. It's that there's a third kind of variable, a third factor that's driving both of them, right? So this is the idea of correlation versus causation. We'll get a lot more into that really the last kind of third of the semester, and we start to get some linear regression type stuff. Okay? So, anytime we see things reported, we should be thinking critically about it. And once we have more knowledge about these different statistics, like we didn't really give you any like means or variances or anything here, but once we have a little bit more knowledge about the different statistics we can compute, we can start to think about how people are using those, maybe not to, to be a little bit manipulative, right, of people who don't understand them. Okay? So we're going to be looking at a bunch of different data sets throughout the semester. So I went out and grabbed the Cubs salary data. So I'll try to use sports examples. I'm already using one here, but this is the only one kind of moving forward. We won't have any more today. So, I got this because it's very hard to get proprietary data, right? This is, the Cubs roster, but this could be any company, right? I've got player name. This could be employee's name. I've got the position they are at the company, and I have their salary, right? Just so happens that it's a baseball team. Right? So if I have a data set that looks like this, we're going to start calling the rows observations, right? I'm collecting data on several different observations, right? And each row represents a different observation. Now, if you look at the book, or if you look at some like more stats kind of like department, terminology, they might call these elements, right? I never will because I just don't use that terminology, but you might see that out there. 90% of people would probably call these observations. I shouldn't say 90% of people. There's probably, this might be something in other countries that they might tend to use elements a little bit more, but I'll always kind of reference them as observations, these different rows. So for each one of these observations, we're then going to collect information on different variables, which are our columns, right? So I've got the variable salary, and I've collected it for every single observation I have here, or every single player I have here, person. Okay? So our rows are observations, our columns are going to be our variables. Right? So we've got different types of data, different types of variables that we can collect data on. Right? So we'll have 2 main categories, and then within each of those categories, we'll have 2 like subsets of categories. So the first main category is qualitative. Sometimes you can kind of think about this as categorical data. So qualitative data is any variable that we're collecting information on that is non-numerical, right? So descriptive word, right? So we think about these as non-numerical or words or qualitative variables. So this would be something like if I had a used car data set, I would have the color of the car. That's just a word, right? Blue, silver, whatever. Okay? So it's a non-numerical value. Quantitative variables are going to be numerical. All right, so quant, I think maybe up to this point, you've probably heard this mentioned before, like a lot of times, quantitative methods, quantitative analysis. Quant is numerical. Okay? So if I had that used car data set, something that would be quantitative would be maybe the mileage on the car, right? You know, we could think of probably a myriad of other examples that would be qualitative or quantitative, right? But the main difference there is qualitative, I think about as words, quantitative, think about as numerical. Questions up to this point? Probably not, but all right. So we can break these down a little bit more. So underneath the kind of category of qualitative variables, we have nominal variables. So nominal variables are qualitative, so they are going to be words, non-numerical, but they have no real intrinsic value to us, right? They don't allow us to say that, well, this observation could be ranked above another observation based off the responses we see. It does give us information, but we can't like rank order the observations, right? So this would be something like, you know, I collect hair color, right? You know, collect gender, I can collect the baseball positions, right? Those were words, starting pitcher, first baseman. I can't necessarily rank order the observations. It's just a characteristic about that observation. Okay. So, is there anything else I want to say here? No, not really. So nominal variables, not overly very useful. They're probably the least useful of all types of variables. But we'll kind of see moving throughout the semester, we still can use them to make some statements about different data sets. So you kind of think about going back to that roster, right? Name and position would both be kind of nominal variables, right? They're qualitative, they're just words. I can't rank order the variables based off of them. Right? Ordinal variables are still qualitative, but they give me a little bit more useful information, right? They allow me to kind of rank order the observations. So what are some examples of this? So think about at the end of the semester when you kind of fill out your student evaluations, right? You choose any one of the questions. But here I chose overall the instructor was an effective teacher. You can go from strongly disagree all the way to strongly agree. So these are just word responses, non-numerical responses. But I know that somebody who strongly agrees with this statement thinks that the instructor was better than someone who disagrees with this statement, right? I can rank order the observations based off of just this word response, right? This ordinal variable response. Now, within each one of these categories, everybody who strongly agrees, I can't say that one person strongly agreed more than the other. So it still has its limitations here because it's a qualitative variable, but it does allow me to rank order people who had different responses. Okay? Another example might be education levels, right? I could say, you know, someone with a college degree has more education than someone with only a high school degree. I can kind of rank order based off of that, you know, but within everyone who has a college degree, there's no way I can really order those observations. Excuse me. Any questions on anything up to this point? So we've got two types of qualitative variables, ordinal and nominal, right? We also have two different types of quantitative variables, right? I guess I have one more example. So for the ordinal variable, I think I use this later on, so I think this is what I put in here. Letter grades are another good one, right? If I can't observe the percentage grade that someone got in a class, but I can see their letter grade, well, I can't say that, you know, someone who got a B-, I don't know if they got an 82 or an 81, but I know that someone who got an A- did better than someone who got a B, right? I know that, you know, B+ would be somewhere in between those two, so I could rank order these students based off of just the letter grade, even if I can't actually see kind of what their percentage grade was in the class, okay? So one data set that we'll use a little bit later on in the semester, I have like every student that I've ever had in my stats courses, I stripped the names out of it so I don't see them in the data set, but I kind of have what their grade was in the class. So I can kind of look and see, all right, how many people got A's over the past 6 years, how many people got B's, so on and so forth, all right? So those are our two qualitative variables. We're also going to have two quantitative variables. So the first one's going to be discrete. So discrete variables are going to be when we can see a numerical, so it's quantitative, right? But there's going to be gaps in the numbers that we can see, okay? So think about it as like if you were asked the number of siblings that you have, right? you could say 0. You could say, I think I left 0 out here. I don't know why. I could say 1. I could say 2, 3, 4, whatever the highest, whatever the newest TLC family they probably have some dumb show about, right? But hopefully someone doesn't respond with like 1.5. Right? Maybe you consider, I don't know, steps or step brothers, sisters. So maybe a better example is the number of children in a household, right? There's either 0, there's 1, there's 2. Hopefully nobody responds with 2.5, right? We don't want half a kid in a house. So these are good examples of finite. You can only see integers. There's gaps in between the responses we could see for these different variables. We'll look at a lot of survey data. They'll ask people like the number of days in a week they do a certain activity. Here, I think I chose the one they consume alcohol. So, once you do something on a day, you've done it 1 out of the 7 days, right? Once you do it the second time on a different day, you've done it 2 out. You can't do it on like half a day, right? If this is the way that the question is phrased. So discrete variables, we'll see them quite often. And they're very useful, right? We could rank order the observations very easily with the discrete variables. But we do have these gaps, right? So this we call discrete variables. Nice kind of visual. I could see 1, they could see 5, they can't see 7.4, right? Any questions here? Shouldn't be anything too crazy. The other type of quantitative variable we have, so it's numerical, is going to be continuous. Right? So a continuous variable just means we can see this variable be any number, right? So think about if it's a truly continuous variable, how many possible responses could I see? I could see any number. The number of possible responses would be infinite, right? Even if I could only see, like, let's say I had states and they were reporting the proportion of their population that, well, we'll say was vaccinated. So proportions, which we'll talk a little bit more in a second, can only be between 0 and 1. But even between 0 and 1, there's an infinite number of possible values I could see, right? So a truly continuous variable, right? We could see an infinite number of possible responses, right? There's no gaps in between, right? It might start and stop at a certain point, but in between that minimum and maximum value I could see recorded, there's an infinite number of possible responses. So some examples might be if I had, a very precise measurement tool, I can actually get height and weight out to whatever decimal I want, right? Specifically weight, there's like, weight, what do they call them? They submerge you in water and they can, using different equations of physics of the displacement, you can actually get it out to whatever decimal level you wanted the weight of an individual, right? So those would be really nice examples of continuous variables. Okay? We could also use salary. We'll use this one quite a bit. Now, think about the number line. We could see 2, we could see 5, we could see 6.41537. Right? We can see any possible value here. Now, sometimes I'll get a little bit, well, before I say this, or any questions over this kind of difference. So sometimes I get a little bit of a pushback here when I say salary is a continuous variable. So why could you argue maybe that salary is actually could be considered discrete? Remember, discrete just means that there's gaps in between the possible responses I can see. So what's the lowest possible salary I could see? 0. Right? What's the next highest? 1 cent. Can I see half a cent? We don't have a denomination for that, right? And so you might think of salary, you want to be theoretically like correct. There are very small gaps, right? Because we can only see things out, there are gaps between every second decimal value, right? But for the sake of what we're doing in this class, and like we could dive into here a little more. If we did have something like salary where it stops at 2 decimals, as long as we have a large enough number of observations, we can treat this as a continuous variable, and none of our what we need for things to be true once we start talking about like standard normal distributions, nothing will be violated. So for the sake of this class, anytime you see a variable that has a decimal associated with it, we can treat that as continuous, right? We'll have large enough data sets where we're going to be okay with that. Okay, so maybe a better way to think about it is discrete, is when you only see the integer values. And then continuous is anytime you see decimal values associated with the number, the variable. Okay. So any questions? So we got 4 different types of variables: nominal and ordinal, which were qualitative, and then discrete and continuous, which are quantitative. Okay. So we go back, I think that salary variable, I had it rounded just to the integer here, just because I'm easier to look at on the screen, but that would be an example of a continuous variable, right? We can actually get salary out to whatever decimal we want. In fact, I try to mention movies you should all see. One time I had someone actually, before I even mentioned it, say, well, salary is not, just isn't continuous, it stops at the second decimal. You should all watch the movie Office Space if you haven't ever seen it. It's hilarious. It's it's pretty old now, but the whole premise of the movie is that if you actually look at pay stubs, often you're actually not paid. It's not limited to the second decimal. Like everything's electronic. You can actually be paid out to whatever decimal they want. So they start like chopping it off. So people only are getting paid like to the second decimal, and they're storing like these fractions of pennies in this bank account. Well, if you do this enough times, right, fractions of pennies can add up to thousands of dollars. But anyways, you should all watch that movie. It's hilarious. I made it sound really boring. It's actually common. So we've got different types of variables. We also have different types of data sets. Okay. So don't worry too much about writing down kind of the definitions here. I'll give them to you, but and then I'll show you examples, which I think will kind of make it, hit home a little bit better. So cross-sectional data, which is more often than not what we'll have, is when we've got several different subjects, so maybe several countries, several different individuals, and we're recording different variables, but at one point in time. So this would be like if I was collecting the GDP of 50 different countries, but all in 2015, right? Then we've got time series, which is one subject recording a variable at several points in time. So maybe I've got the United States, and I want to collect their unemployment rate at several different, the last 20 years, right? And then I've got kind of combining the two together, which is panel data. So this is where I have multiple different subjects and I record data at multiple different points in time. So this might be, I collect GDP on every single country and I record it for the last 10 years, right? So several subjects, several points in time. So cross-sectional data would look something like this, right? I've recorded this data all from 2011. I've got all these different countries, and I can collect multiple variables. It's just that they're all collected at the same point in time. So I have GDP and then primary and secondary education expenditures, but all of them were recorded in 2011, right? So one point in time, I can still have several different variables being collected. That's cross-sectional data. Time series data is going to look something like this. So I've got just the US's unemployment rate, but I've got it collected at multiple points in time. Right? I don't know if we'll get there today, but if not Friday for sure, I will show you how in Excel we can actually create some pretty useful graphs with time series data. I then going to have the combination of the two, which is our panel data set. So here I've got ISTEP scores. I've got a bunch of different variables here, but specifically ISTEP scores for 3 different students here, right? But for each student, I've got them recorded at 3 different time periods, right? So I've got multiple subjects, multiple points in time. This is my panel data set. Now, we won't probably use these as much in this class. Maybe towards the end of the semester, we'll see more examples with data sets like this. But if you're kind of continue, if you end up kind of liking some of the stuff that we do in here, you want to learn more about statistics, which the landscape out there right now is as much information and knowledge you can have about data, the better off you're going to be. But in the next level of stats, we would really exploit panel data sets because we can do some things with them that we can't do with others, right? So yeah, this is another example of some data we might look at. I think this is, I think you're old enough now where none of you would have been, oh, maybe this one's grade 8. If you would have been in grade 8 in 2011, I have a data set with you in it. I don't see your name, but I have your ISTEP scores if you took the ISTEP in the right? So those are our 3 different types of data sets. We're then going to talk about something that doesn't really, it's not going to come up until next week, how this really plays a role in the different statistics that we're going to compute. But for now, we'll just talk about the issue of we might have population and we might have sample data sets. So what are the difference between the two? Right? So population data would be that I had recorded whatever variable I'm looking at for every single person in whatever group I'm trying to kind of make statements about. So if I wanted to say, calculate the average income in the United States, population data would be that I had the income of every single person in the United States. Right? So population data sets tend to be very large, right? Sample data sets, sorry, I forgot I had the census here. I don't know, I probably don't need to waste a lot of time, but like we only usually get population data for something like the average income in the US by taking something like a census, right? So we only do this every 10 years, but it's to collect different information on the population of the United States. Now, in the meantime, we might want to say, okay, well, the census tells me maybe the demographic information about the US every 10 years, but in between those 10 years, I might want to still say like, well, what's happening in between, right? Well, I'm not using a census, but I can go out and grab a small subset of the population and create a sample data set, right? It's not going to be as many people, right? But I could use that sample, and we'll talk later on in the semester about how we ensure that sample is not going to be biased and it's going to look similar to the population, right? But for now, we'll just know that once we have that sample data, we're going to use that to calculate different statistics and then use those statistics to make inferences about the population as a whole. We don't often have population data. Sometimes it's impossible for us to get it. But if we have sample data, right, that's the best we can do. We'll use the information from the sample to make inferences about the population. So that terminology is actually, I've got it later on, but that idea would be statistical inference. I'm using the sample to make statements about the population as a whole, right? And I'll come back to this here in a second. But I jumped the gun. So it's hard to get population data for two reasons. One, it's just very expensive. Like that's why we only run the census every 10 years, right? It's very difficult to do all this data collection, then to gather the data, analyze it, right? And so it's sometimes, not worth spending all the money if we can get a smaller subset, get a smaller sample data set, and then make inferences about the population. It's also sometimes impractical, right? So a really good example of this would be, let's say I wanted to measure what the current obesity rates in the United States are. I try to go out, contact doctors, or kind of measure or weigh people, and I have to get, the weights of every single person in the United States, right? To calculate my obesity rates. By the time I've collected everybody's weight, what's probably true about some people's weight? Let's say this took half a year. It's probably changed by then. Well, now I don't have current data, right? So sometimes it's just not practical. It's just not possible, right? And honestly, if I go out and collect 20,000 people's weights, that's probably going to be a pretty good measure of what the overall population obesity rates are as well, right? So, or when I say weight, we need more information to calculate obesity rates, but you get the general idea, right? So, a lot of times we're just going to have sample data. We'll use either population data or sample data to come up with descriptive statistics that tell us things about whatever variables we're interested in. And here, some of these descriptive statistics, the way that we calculate them will vary depending on if it's population or sample data. So like I said, we won't really address that until next week, but that's why I'm bringing this idea up now, just so that we're used to this terminology of population versus sample data, okay? And then that statistical inference, I've kind of already mentioned what that idea was. So any questions up to this point? We'll start actually doing kind of the first computation or kind of the first statistical analysis here. Good with everything so far? All right. So the first thing that we're going to do when we're looking at data is come up with frequency distributions, okay? So all a frequency distribution does is it takes a variable, it looks at all the possible responses we could see for that variable, and it counts the number of times we see that response in our data set. So if I'm thinking about grade here, and I kind of got rid of pluses and minuses to make it a little bit easier, I'm going to get my frequency distribution. I would count the number of students in this data set who got A's, the number who got B's, C's, D's, and F's. I probably should have also included like incompletes, but we don't see any incompletes here, so we don't have to count them. So all I would do is go through and say, okay, the frequency or the number of times I saw the response of A was twice. So for A's, I have a frequency of 2. For B's, I have a frequency of, so there's 3 students. C's, there's 2 students. D, there's 1. F, there's 1 student. What I have on the right-hand side, that is my frequency distribution, right? I had 5 different possible responses that I could see for this variable of letter grade. And I got the count or the frequency that I saw in this data set of each one of those possible responses. Okay, so this frequency distribution very quickly shows me like, oh, the majority of students in this class are getting a C or better. The highest, the most frequent or the most common grade is a B, right? And D's and F's are not very common, right? So the frequency distribution gives me some some information very quickly, right, about this variable from this data set. Now, this is an easy example, right? It was kind of easy to see this to begin with because I only had 9 observations over here, right? But I had a much larger data set. So imagine that data set I mentioned where I have every student that I've ever had in stats and I have all their letter grades, right? I forget what the count is. It's somewhere like up around like 700 students now for just those stats courses. I don't want to go through by hand and count those. I don't want to come up with that frequency distribution by hand, which is why on Friday, I'll kind of show you how do we do these frequency distributions in Excel, right? Because Excel can do this very quickly for us, right? We can come up with a frequency distribution very quickly in Excel. Now, I can do it quickly here if we've got a small data set by hand. But if I had 700 observations, I don't want to go through and count the number of A's, B's, C's, D's, and F's. That would take me a while. Right? So once we have this frequency distribution, we could then move to the next thing, which is a relative frequency distribution. So all a relative frequency distribution does is it takes each possible response, right? And it takes the frequencies for those responses, we divide them by the total number of observations, excuse me. And basically a relative frequency, another way we can think about it is it represents a proportion. I'll give you an easier example. So let's say we had 100 students. And I go through and I find that 10 people out of the 100 got an A. My relative frequency would be take that frequency of 10 students who got an A, divided by my total number of observations, which would be 100. So I would have a relative frequency of 0.1, or the proportion of students who got A's would be 0.1. So relative frequency is really the same, it's kind of synonymous with the word proportion. What's the lowest relative frequency I could ever see? Well, what's the lowest frequency I could ever see? 0. So what's the lowest relative frequency? 0 divided by anything is still 0. So the lowest relative frequency I could ever see would be 0. Or the lowest proportion I could ever see is 0. What's the highest relative frequency I could ever see? What if every single person that's ever taken my class got an A? It's not true, but what if it was? Well, if 100 students got A's out of 100 students, my relative frequency would be 1, right? So my relative frequency or my proportion has to be somewhere between 0 and 1. Okay? So I've got a sample data set over here where I kind of am giving you the frequency distribution, right? So there's this huge data set. You can go out, the CDC will give you the frequency distribution. I don't think you have to actually make a request to observe the actual observational level data set, but they collect information on the causes of death, right? So they look at death certificates and then they kind of compile this huge data set. And like I said, you can request access to it. I mean, it takes a while and you have to fill out a bunch of paperwork, but you can get the frequency distribution of this huge data set that has every single death in the US. So I put the link up here. This is someone that was like working with the CDC, and this is preliminary data, right? So this is for 2021. So it usually takes them a long time to work through all these certificates, but this is the preliminary data they have for death data. So For instance, if you go to that link, I think the COVID-19 one has an asterisk next to it because a lot of them haven't been checked to ensure that they were primarily from COVID. But this is the preliminary data. Okay? So I've got these frequencies, right? To turn them into relative frequencies, all I'm going to do is take the frequency, say the number of people who died from heart disease, divide it by the total number of deaths that I had, and that'll give me that relative frequency, or the proportion of people last year who died from heart disease. Right? Now, I rounded these to the second decimal, right? The actual values are go out, go out several decimals. A lot of times in this class, anytime you're asked to calculate something, usually I'll specify like keep it out to 2 decimals. On the Connect homework, sometimes they'll tell you to keep it out to the 3 or 4 decimals. But really, once we start working in Excel, we can see like we don't really have to worry about it. Excel stores it out to wherever it stops, right? But here, just to make it look a little bit nice, a little bit cleaner, I kind of rounded these to the second decimal. So once I went through and we got every single frequency, we divided by the total number of observations, I got the relative frequency for every single kind of cause of death. So very quickly, I can look at this relative frequency distribution and see the proportion of people that died from heart disease and cancer is much higher than any other kind of cause of death here, right? 0.21 and 0.18 are quite a bit higher than any of these other values, right? This is always shocking me, like unintentional injuries seems relatively high to me, but like the portion of people dying from them are 0.06. And then we have our catch-all category here, which was other, right? So there's any other cause of death. Right? So we can kind of see like the what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The top 11 causes of death, right, account for about 75% of overall deaths, right? Or I say 7, or proportion of deaths 0.75, right? Because the other category is 0.25. Now, if I look at these relative frequencies, what should they all add up to? 1, yeah. Right? So think about why. How did I come up with the total deaths? Well, I would add up the frequencies, every type of cause of death. Well, if I add up my relative frequencies, the numerators are just my frequencies. So I know those will add up to the total number of deaths. I divided them all by the total number of deaths. So any number divided by itself will always be 1. Now, this is only if I've accounted for every single death that has occurred there in my frequency distribution, which we're assuming that the CDC did. Or I shouldn't say CDC, the person that was working closely with the CDC did. Okay. And I think that I had my Zoom thing down here, right? So you can kind of see there, the total should always be 1. So if you're calculating relative frequencies and you ever get, where do I want to put this down here? If you ever get anything other than 1 when you add up your relative frequencies, you know you made a mistake. All right. Any other questions on this before we keep moving? Where are we at in time? Oh, okay, we're pretty good. Okay with this? All right. So the next step is we don't often talk in proportions. Occasionally we do, but, and I think I even slipped up a little bit earlier. More often than not, we're going to talk in percentages. So once I have a relative frequency or once I have a proportion, to get a percentage, all I'm going to do is take that relative frequency and multiply it by 100. Think about it this way. If I had like 50 of the 100 students got A's, the proportion of students who got A's would be 50 over 100, or the relative frequency of 0.5. But very easily, we know that 50 out of 100, that would also mean that 50% of the students got A's, right? So take that relative frequency of 0.5, multiply it by 100, that would kind of give you that 50%. So we kind of think that way a lot, but it's like we're doing it kind of almost like subconsciously kind of thinking about these percentages. Like I said, we generally talk more in percentages than in proportions. And so usually a lot of times we convey data in percentages as opposed to proportions more often. Right? But this is, I think, pretty easy. Or another way to think about this, if I want to go from a proportion or a relative frequency to a percentage, I'm just moving the decimal 2 places. So, I can think about, a sample question, like once we start having these online quizzes, which I'll probably post one after class on Friday. So you'll have to complete it before we start class on not Monday, but the following Wednesday. Right? So you have a lot of time for that because we've got Monday is on. So one question you might see in an online quiz is like after we work through all this material today, it might look something like this, right? So if I gave you all these frequencies, I gave you this frequency distribution, and this is for an older time period, I had the kind of leading causes of death. How would I come up with my percent frequency for malignant neoplasms here, which is essentially cancer? I would take that frequency of about 4.4 million, then do what? I want to turn this into a percent frequency. I first need to get a relative frequency. How do I do that? I'll take my frequency and divide it by a total number of observations. Right? So 4.4 divided by about 16.6. I'm roughly doing some gross rounding there. That would be about 0.25. And then to get my percentage, I would take that relative frequency and multiply by 100. So I should get around 25%. I think if I actually plug these values into my calculator, I'm probably going to get 26.8. Right? But so I would give you these 4 possible responses, right? You would do the actual work. Hopefully you would choose the right answer. Right? And I could do this for any cause of death here, right? Just take the frequency, divide it by the total number of observations, and then multiply it by 100. Any questions on this? Yeah, this shouldn't be too bad. What are we at in time? We got what, 10 minutes left? So we can also do things like bar and pie charts. So once I have these frequency distributions, it's great. I can look at the numbers here and see like, oh yeah, a much higher percent of deaths are coming from heart disease and cancer. And you know, look at all the other various causes of death here. But right, I might want to go do a nice visual, right? So you've probably seen like bar pie charts maybe already. Like, you know, I feel like pie charts are like something you do in like high school science classes or something like that. But right, we can do it in Excel very quickly. Right. So I'll show you how I do it in Excel next class, but I do want to kind of, you know, give you a little bit of an insight into what this is going to look like. So let's say I had that 2021 death data. I have my frequency and I have my percent relative frequency, right? So I turn these into percentages. I could graph them as a bar graph. So all I'm going to do there is for each cause of death, I'm going to put like a category on the x-axis. So I'll write heart disease, and then I'll draw a bar up to whatever the frequency was for heart disease, right? So I'll take heart disease and then I'll draw a bar that goes up to 690,000. I'll then do my next cause of death, which is cancer. Its frequency was just about 600,000. So I draw a bar up to 600,000. I continue to do that for every single possible response I could see from my variable. And then I have kind of this visual of the distribution. Now here it's kind of a weird one because instead of really doing every possible cause of death, we had this catch-all category of other. But this is a nice kind of pretty quick visual of like, oh yeah, about 700,000 people are dying from heart disease, about 600,000 from cancer, so on and so forth. Right? And you kind of quickly see from the bars, like those are the thing that's killing people the most. Right? So maybe if I'm like the government, I'm starting to direct funds towards those things. Okay? Now, if I instead did a bar graph with relative frequencies, what's going to change? I'm still going to have the same categories. It's just that my y-axis instead of frequency will now be my relative frequency. So it's going to be between like 0 and 1. But the relative size of these categories isn't going to change. Right? If I multiply anything by the same number or divide anything by the same number, the relative size doesn't change at all. Right? Think about it this way. 2 is half of 4, right? But if I divide 2 and 4 both by 2, I now have 1 and 2. 1 is still half of 2, right? So anytime I divide by the same number or I multiply by the same number, it doesn't change the relative size of those numbers, you know, or doesn't change the ratio, I guess you would say. So if I were to do the same graph, but I were to use my relative frequencies, so do heart disease, draw a bar up to 20.57. Then Cancer, draw a bar up to 17.83. What's going to be true is I have the exact same, like the graph looks exactly the same. It's just that my y-axis has changed, right? And now I can quickly see instead of the number of people dying from heart disease and cancer, I'm getting the percent of people that die from heart disease and cancer. Any questions on that? I can also do a pie chart, right? And this is the larger the slice of the pie, the higher the percent frequency here. So I've got kind of my legend right here. It's another way of kind of turn this into a nice visual. I'll show you how we do all these in Excel next class, and we'll also start to deal with some quantitative frequency distributions. Okay? So get out a little bit early today. Make sure you get registered for Connect. For that Connect and SmartBook. One thing I don't know if I mentioned on Monday is you can get a 2-week free access, I believe. And then after the fact, if you want to buy it later, it syncs everything up. So get registered for that. Get that first SmartBook assignment out of the way. And I will see you guys on Friday.